Today, we are going to discuss a new lesson, what we call electromagnetic induction. Yesterday, we have finished the magnetism. Last lesson was terrestrial magnetism and the magnetic elements at a place and everything we have discussed. Today, we are coming to this topic. This is electromagnetic induction and AC current. This is the last lesson of the series. That also we will finish very soon. This is electromagnetic induction. So electromagnetic induction is very important, right? Because after this we will go to AC. To understand AC, you must have an idea about electromagnetic induction, right? First of all, in this topic, we'll have discuss what is magnetic flux. Electric flux you have studied in the first class, electrostatics, Gauss theorem and all. When we were discussing, I told you what is electric flux. What is electric flux? Do you remember? It is the electric field lines penetrating through an area along its normal when it is placed in a uniform electric field. Understand? Magnetic flux also can be defined the same way. It is the magnetic field lines penetrating through an area along a normal placed on the plane when the plane surface is placed in a uniform magnetic field, right? Flux density in the case of magnetism is defined by the total number of electric field lines penetrating through unit area, right? If ds is an area, then the magnetic flux through the total number of lines of force passing through that area is B dot ds. It is B dot ds that we have discussed in same way we have discussed in electrostatics, that is E dot ds. In this case, it is B dot ds, right? So there must be an area that must be placed in a magnetic field, and the magnetic field is full of magnetic lines of force. The number of lines of force, the total number of magnetic lines of force penetrating to an area placed in the uniform magnetic field through its normal is called flux, total flux. Right? As we wrote electric flux as phi E, here you will write phi B, you will write. It's called as phi B, we will write, right? Phi B. Phi B is equal to B dot ds. B dot ds, where B is the magnetic flux density and ds is the area. So this can be written as simply BDS cos theta also we can write. BDS cos theta, where ds is the surface vector, right? So this much only you need to understand. Magnetic flux density phi B denoted by phi B is equal to BDS cos theta, right? So from the very relation itself, it is clear that the magnetic flux density, this one here d phi B, right? Because it is a very small area ds. D phi B is equal to B dot ds. That is equal to BDS cos theta, right? Because we are taking a very small area ds. So we can, for reference, we can go to that first lesson, Gauss theorem. When I explained the Gauss theorem, I might have told you about how to calculate, how to derive the relation for electric flux, right? We took a very small area of value here, ds. Ds is also called a surface vector. All these things explained there. Here there is no need of much explanation. That is why directly I am coming to the flux, then magnetic flux. Through a small area, it is given by d phi b. D phi b is equal to B dot ds, that is will be ds cos theta. Very clearly, flux density d phi b is maximum when theta is equal to 0. Because flux density d phi b through a small surface is depending on cos theta. When theta is equal to 0, then the flux density is after the total flux is maximum. I can draw a diagram also here. Suppose this is an area. This is an area like this. This is the normal placed on the area denoted by vector ds. And this lines of force, that means it is placed in a magnetic field, and this is it is like this, it is penetrated. These are B only, right? B only. In this case, what we see is that the magnetic field lines are penetrating through this area ds. This magnitude of this area is ds, and this can represent a vector, what is called a surface vector ds. In this case, theta is equal to 0. Theta is equal to 0. In this case, you will see that the flux is maximum because theta is equal to 0. Why theta is equal to 0? Because the surface vector is in the direction of the flux density. It's the intensity of magnetic field or the direction of the lines of force, magnetic lines of force. Theta is equal to 0. In this case, you must remember one more thing in that when theta is equal to 0, that means the flux density direction, yeah, the intensity of magnetic field direction, yeah, the direction of the field lines when parallel to the surface vector. Surface vector is a normal placed on the surface. Both are parallel, theta is equal to 0. Then you will see that the magnetic field lines are perpendicular to the plane, right? Magnetic field lines are perpendicular to the plane. Then the perpendicular placed on the plane is parallel to the field lines. Then the maximum number of lines of force will pass through it. Flux is maximum. Maximum flux is given by simply BDS you will write. Because cos theta is equal to cos 0, that is equal to 1, right? Then another case is there. That is, suppose that this is the plane. This is the plane here like this. This is the surface vector as shown here. And this is the field lines. Field lines are like this. Field lines are like this. This is B. That is vector B makes an angle 90 degree with the ds. 90 degree with the ds. Then according to this relation, d phi b is equal to bds cos theta. Theta is equal to 90 degree. Then d phi b is equal to 0. Flux through the surface is equal to 0. It is very clear. Why? Because the lines of force are passing over the surface. It is not penetrating. So, in the case when the field intensity direction makes an angle 90 degree with the surface vector is a practical way how we apply surface vector. Surface vector is a perpendicular placed on the surface. Then the flux through the surface is equal to 0. So these are the things about flux, right? If it is a very big area of A, a large area is placed in a magnetic field of intensity B, then total flux through that large area is given by phi B, we can write. Phi B is equal to BA cos theta. BA cos theta. Right? In the place, in place of area, you can keep a coil also. Right? If it is a coil having an area, it has a plane area. It is a rectangular coil has a plane, right? This rectangular coil has n number of turns through that. N number of turns that coil has. Then the total flux is equal to given by NBA cos theta also we can write. NAB cos theta. So simply a plane surface there can be, that can be coil also. Coil having n number of turns also there. When it is placed, the general expression for flux through any area, a coil having n number of turns is given by NBA cos theta or NAB cos theta. Flux is measured using, magnetic flux is measured using a unit called Weber, right? Weber. So flux phi B is measured using a symbol of Weber is WB. And its dimensions are, of m L square T raised to minus 2, m L square T raised to minus 2, e raised to minus 1. These are the dimensions of this physical quantity. This is what is called magnetic flux. So magnetic flux is nothing but it is the total number of magnetic lines of force penetrating through an area along its normal when it is placed in a uniform magnetic field of intensity B, right? So magnetic flux density is denoted by the letter capital B, right? This is about. So flux you understood. So knowing the flux only, the further thing I can speak. Otherwise you will not understand anything, right? So magnetic flux is very important. Magnetic flux is nothing but it is the total number of magnetic field lines penetrating through an area placed in the magnetic. Next is Faraday's laws. So Michael Faraday was the scientist for the first time study all these things. And Michael Faraday's discovery is very, very a landmark experiment, right? Michael Faraday's experiment led to the production of electric current. AC current or DC current can be produced, and this discovery was made first time by Michael Faraday. So Michael Faraday put forward two laws, right? The first law and second law. According to the first law, Michael Faraday's first law, whenever there is a change in magnetic flux linked with a conductor or a coil, EMF is induced in the coil. There must be first flux variation. Flux variation can take place due to the relative motion between a magnet and a conductor, or a magnet and a coil. Coil of any shape there can be. When a coil is placed somewhere and a magnet is in relative motion with respect to the coil, then in the coil, due to change in magnetic flux, EMF is induced. EMF induced means energy is produced. When an EMF is induced, the potential difference is created at the two ends of the coil. If the coil is connected to if the coil is connected to a galvanometer, then the galvanometer starts deflecting. So that is given here. So there are two conditions there. One condition is like this. This is a coil and this is a galvanometer connected, right? A coil, you can see it. And a magnet is made to is taken towards, this is north pole and this is south pole. And it is fastly approaching. Fastly approaching means magnetic lines. Then there were no magnetic lines of force passing through the coil. All of a sudden, when the magnet is brought towards it, through the different ends of the coil, the magnetic lines of force starts penetrating. And also it is increasing as the magnet is coming towards it. So flux linked with the coil changes. That is due to what? Due to the relative motion between the magnet and the coil. If the coil is kept stationary and the magnet is moving towards it, flux linked to the coil changes. Right? The coil is kept stationary and the magnet is moving away from it, then also there will be change in flux. Right? In both the cases, EMF is induced in the coil. But remember, in these cases, both these cases, the EMF induced will have some different effect. Effect will be different. And because the current flowing in the closed circuit in both the cases will not be same, but different, because the effect of the EMF produced is different. Suppose in one case, suppose the current is like this, the current is like this. In the other case, the current will be in a different direction. Suppose this is the coil in this case. So this magnet is taking away. This is north pole and this is south pole. So naturally, there was a large amount of magnets of force passing through this coil as the magnet was coming towards it. When the magnet was approaching it, okay, the flux was increasing. Now it is taking away from that. The flux is decreasing. In that case also, an EMF is induced. So in both the cases, we have seen that the coil is stationary and the magnet is moving. The other situations also can be possible. You keep the magnet stationary and the coil is in the relative motion, then also EMF is induced in the coil only. And due to the change in magnetic flux, EMF induced, and this hence a current starts flowing in the circuit. The galvanometer starts deflecting. In the second case, you will see that the current is in the opposite direction as shown in the figure, because EMF created will have a different effect. This is what is called the first law of electromagnetic induction. So according to first law of electromagnetic induction, whenever there is a change in magnetic flux linked with a conductor of any shape or a coil having any number of turns, due to change in magnetic flux linked with the conductor or the coil, EMF is induced at the two ends of the conductor or what do you call, in a coil. EMF is induced and hence a current starts flowing in the circuit. That is shown by the galvanometer. This is what is called electromagnetic induction. The EMF induced is called induced EMF, and the current so created is called induced current. So we have studied many things today. What do you call the flux? I have said the general expression for magnetic flux for a large area is dA cos theta, right? If that is a conductor of large area. If it is a coil having n number of turns, then flux through that coil, through the plane of the coil, is given by phi b is equal to NBA cos theta, right? So flux variation when takes place with respect to conductor or a coil, EMF is induced in the coil. This was the first law, right? First law is very clear to everybody, right? Next is second law. According to Faraday's second law, the magnitude of the EMF induced in the coil is directly proportional to magnitude of the EMF induced in the coil is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux, right? The EMF induced and the magnitude of that is directly proportional to the the change in magnetic flux is directly proportional to EMF induced in the coil. That is EMF. EMF E is directly proportional to EMF E is directly proportional to change in magnetic flux in the coil. So change in magnetic flux I can write N phi 2 minus N phi 1. Here N phi 2 I am taking because suppose the coil has N number of turns at any instant, right? Through a single turn, the flux is equal to phi 1. Then to n number of turns, the flux variation is equal to n phi 1. The product of flux and the number of turns the coil is called flux linkages. Right? Change in flux. Suppose at any instant the flux through the entire coil turns is equal to n phi 1. And another instant the flux variation is n phi 2. Then change in flux is equal to n phi 2 minus n phi 1. Suppose this change takes place in a time t. This is called rate of change of magnetic flux, right? Or E is equal to a constant k into n phi 2 minus n phi 1, the whole divided by t also we can write. Where k is a constant, the value of k is all in the XY system, the value of k is always taken to be equal to 1. In that sense, we can write E is equal to n phi 2 minus n phi 1, the whole divided by t also we can write. Am I correct? The same thing can also be written as equal to n into d phi by dt. N into d phi by dt, because n into phi 2 minus phi 1. For a small interval of time, the flux variation is equal to small value. Therefore, n into d phi by dt, suppose the name duration of time dt seconds, the change in flux is given by d phi. In that sense, we can write EMF induced is equal to n into d phi by dt. Right? This is mathematically correctly written as equal to E is equal to minus n into d phi. There is a negative sign also always coming with this relation n into d phi by dt. So n in this negative sign represents Lenso's law that we'll discuss later on. Lenso's law mathematically. So today onwards we go to a relation E is equal to minus n into d phi by dt. N represents what is called Lenso's law mathematically. So this is second law. So according to Faraday's second law, due to change in flux, EMF is induced in the coil. The EMF induced in the coil is directly proportional to the change in flux. Change in flux means in final flux minus initial flux divided by t. So in numerical problems also it is given there. So suppose if it is given as an equation, then then EMF is equal to d phi by dt. That means by differentiating the expression, you will get the total EMF produced in the coil. EMF is in volt. The unit you will write as equal in volt. You can write. If it is an equation, you have to differentiate it. So this is about. Am I correct? Okay. Simply we can write E is equal to d phi by dt also. If the coil has only one number of turns, then E is equal to d phi by dt. D phi by dt also we can write. Am I correct? But I is equal to E by R. But I is equal to E by R only. But where R is the resistance of the coil. Therefore, I is equal to E by small e by R. That is equal to this divided by R. that is equal to d phi by dt into 1 by r also we can write. Am I correct? But I is equal to dq by dt. Therefore, dq by dt is equal to dq by dt is equal to right d phi by dt d phi by dt into 1 by r. So because I is equal to dq by dt. Therefore, the value of charge in the coil, the amount of charge passing in the coil is given by dq is equal to d phi by dt into 1 by r into dt. We can write this and this cancels. You will get this is equal to d phi divided by r also we can. So this is another equation, different equations in this. Yeah. So magnitude of the EMF generally given by E is equal to N into d phi by dt. So remember this. N is the number of turns in the coil. If it is a coil that is placed in a magnetic field and it is varying its position, relative motion is there, then the flux linked with the coil changes and EMF is induced in the coil, right? If either of the both the things, that means magnet and the coil, both are stationary, then there is no EMF is induced in the coil. Because when there is no relative motion between the coil and the magnet, the flux changes is not taking place. So for EMF to be induced in the coil, what is necessary? There must be change in flux, right? This is what I want to speak about in this particular subject, this particular topic. So we have explained Faraday's first law and the second law that you have seen. According to first law, whenever there is a change in flux linked with the coil, EMF is induced in the coil. Second law says that the EMF induced in the coil, the magnitude of the EMF induced in the coil is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux is N phi 2 minus N phi 1 divided by T, or N into d phi by dt. So this is about magnetic flux and also how EMF is induced in the coil and the two laws of Michael Faraday, everything explained. Next is Lenso's law. According to Lenso's law, the EMF induced in the coil is such that which opposes the very cause of production of the EMF in the coil. Suppose that this is a coil, valvometer is fitted here, and there is a magnet which is fastly reaching towards the coil. So the coil was free of magnetic field. All of a sudden, if magnet is passing or it is moving towards it. When the magnet is coming towards it, the magnetic lines of force starts penetrating through the different turns of the coil. Hence, we can say that flux variation takes place. Due to flux variation takes place, EMF is induced in the coil. Right? Lenses, one scientist called Lenso, L-E-N-S, Lens says that the EMF induced in the coil is such that which oppose the very cause of production of the EMF in the coil, right? Suppose that the north pole is reaching towards this end, A end of the coil. So we can say that in north pole itself is created at that facing end. So what happens? North pole is coming towards it, and here also a north pole is developed. North pole ripple the incoming of the north pole. Work has to be done to push the magnet towards it. This work itself is actually converted into EMF induced in the coil, because EMF is energy only. So energy or EMF induced in the coil is equal to the work done in pushing the magnet toward the coil. Am I correct? So this is what is called Lenz's law. So according to Lenz's law, due to the relative motion between a magnet and a coil, EMF induced in the coil is such that whose effect is such that which opposes the cause of production of the, what is the cause of production of the incoming action of the magnet? The EMF produced in the coil will always opposite. So this is a general condition and understanding we must have, right? This is the situation. Suppose that this magnet is taking away from the coil. Then what happens? Already the magnet was quite near to this coil, and the magnetic flux linked to the coil was maximum. That was increasing. all of a sudden the magnet is taking away from this. Then what happens? Inside the coil, the magnetic flux starts decreasing from maximum to minimum. Then also there is change in flux. First case, from minimum to maximum change in flux was there, and second case, from maximum to minimum the flux variation takes place. Then also an EMF is induced in the coil, but the effect of the EMF produced and the effect will be opposite. You can say that north pole is taking away, then a south pole itself is formed here. South pole attracts a north pole. So for any variation of flux in this, what we have to do is that we have to take away the magnetic north pole away from this space. So this space, yes, south pole is created. South pole attracts it. So we have to do some work against the attractive force due to the south pole produced at the nearest end of this coil. So what this work done is actually stored in the form of EMF in the coil. So this is what is called Lenz's law. So Lenz's law can be explained in terms of flux, in terms of EMF, in terms of current. Many ways Lenz's law can be explained. So Lenz's law is very, very important. Using Lenz's law, one question is most of the time asked in CBSE examinations, right? So that can be explained in terms of flux, you can explain, in terms of EMF, you can explain, in terms of current, you can explain. Anyway, you can explain Lenz's law, right? This is Lenz's law, right? So that is why the negative sign comes up. It opposes the very cause of production of the EMF. That is where we are for now. Actually, magnitude has nothing to do with the negative sign in the expression. E is equal to minus n into d phi by dt. This negative sign has nothing to do with the magnitude of the EMF. But it only reminds us that whenever there is a change in magnetic field into the coil, the EMF induced is such that which opposes the very cause of production of the EMF, right? That idea to give us, to remind us, this negative sign is appearing in the expression E is equal to minus n into d phi by dt. Simply we can write E is equal to simply magnitude. When you write simply E is equal to d phi by dt also, you can write. When you get an expression, you will differentiate the expression and you can find the value of EMF and will write the unit as volt, right? So there are so many explanations here done in this condition. So one is like this. One is like this. Suppose this is the situation, right? There's a wire through which electric current I is passing. Here there is a ring is there. A metallic ring is there. When electric current passes through a circuit, so passes through a wire like this, wire is AB. So I am explaining what Lenz's law, how to explain Lenz's law, and can judge what is the direction of the current in this metallic ring. Everybody knows that Oersted theory, Oersted theorem means when a current passes through a conductor, a magnetic field is produced around. This ring is also placed very near to this current carrying conductor. So magnetic flux linked with this ring can change. You are asked a question in which direction current will be, in which direction the current will be in this metallic ring. I will say this is like this. Because in the case when current I is increasing through this wire, the current produced in the ring must be such that that must oppose the increasing current in the wire AB. Why there is magnetic flux produced in this one? Because the increasing current in this wire AB. Right? So in this case, you see the current will be in the clockwise direction. Why clockwise direction? Then only this direction are opposite each other. So in terms of current also we can explain what you call Lenz's law, right? Current is increasing. So what is the directional current in the coil? The coil is placed very near to the this wire carrying current, and the current in the wire is increasing. Then magnetic flux linked with the coil, this coil, metallic coil can change, due to which a current can be produced in that. The current direction will be such that that must oppose the increasing current, because the magnetic flux in this through this coil is due to increasing current of the wire in the wire. The hence the induced current will be such that that must oppose the increasing current. That is why in this question it is opposite. Opposite. This is the direction, this is in this direction. Right? Suppose that the current is decreasing. In the case when current is decreasing in the wire, then you will see that naturally this will be like this. Right? Anti-clockwise direction. So in the case when current is decreasing, the decreasing current must be opposed by the induced current. Decreasing current is to be opposed means the induced current will be supporting the decreasing current. Because due to decreasing current only, the EMF is induced in the coil and a current is induced. The current induced must oppose the decreasing current in the wire. Decreasing current in the wire means we have to oppose the decreasing current means the induced current must support the decreasing current. That is why in this case the current in the coil is in the what is called anti-clockwise direction. So this can be explained in many ways. Am I correct? So, and another situation in which Lenso's law applied is like this. Suppose that you have a coil here. These are completely explanatory lesson. Suppose there's a coil here. In this direction, suppose that in this direction, the magnetic flux is increasing. Magnetic flux increases in one phase, then naturally an induced flux is created. Induced flux means phi I is created, right? So when there is a flux through a coil, through one phase, if it is increasing, then a counter flux is created, is developed within it. That is what is called induced flux will be in the opposite direction. Because the flux variation through this coil is increasing. Therefore, according to Lenso's law, there must be an opposing flux created linked with the coil. Am I correct? So these are the conditions. Using flux also we can explain what do you call Lenso's law. With the help of EMF also we can explain Lenso's law. In the case of using current also we can explain Lenso's law. So Lenso's law speaks that whenever there is a change in flux linked with a coil, the induced EMF is such that which opposes the very cause of production of the EMF in the coil. So the Lenso's law is very important, and and the other things. Today's lesson is this much only. Other topics we'll discuss tomorrow, right? That I will be coming with a new lesson tomorrow. Till then, goodbye. Thank you very much.